Okay, let's get started. All right, so in our last lecture, we finished talking about chapter 9, okay, which is the capacity of the channel. Okay, and here in the last lecture, we talked about capacity of either channel. In particular, we derived the capacity of the parallel Gaussian channel. Okay, and we argue that so it has wide use in practice, especially for the OFDM system that we are using today. Okay, in Wi-Fi, in 5G, and so on. Okay, and then we start talking about chapter 10, so which is the rate distortion theory. Okay, so that's a lossy compression, right? We covered the lossless compression before, so now we come into the regime of lossy compression, which is kind of used everywhere in practice, right? We use a lot of lossy compression. For example, JPEG is a lossy compression, MP4 is a lossy compression, and so on, right? And so that is pretty important. And also, in machine learning, so we also use this kind of concept a lot. Okay, there's a theory, it's called rate distortion perception theory. Okay, so yeah, this chapter, is the last one, but it's definitely also very important. So for the capacity of a parallel Gaussian channel, so we can, based on, this is still point-to-point, right? So you can imagine this is kind of like a multiple antenna system, but there's no interference among antennas. Okay, it's still one transmitter, one receiver. Okay, so it's still kind of this kind of system. Therefore, so yeah, by saying that, yeah, maybe let me say one more word. So what is the difference between a point-to-point system and a multi-terminal system? Right, so for example, yeah, this may be, we don't have time to cover any of the multi-terminal information theory. So I have some lecture notes online, so you can take a look. I'll upload them. Right, so basically, what we consider here is like this, one-to-one, right? One transmitter, one receiver, right? But when we say about multiple parallel Gaussian, it seems like this, right? It seems like this, right? But it's not multi-terminal. The reason is that so we have the so all of them share the same information. Okay, so you can think as in this way. So each node knows everything. Okay, each node knows all the message, and then therefore it's only like one node. Okay, so of course each of them can send different signals. It's up to design, but it's free to allocate any information there. Okay. On the other hand, let's say if we have this kind of system, right? Let's say so those are transmitters and this is a receiver, right? So this is like our Wi-Fi, right? So when your computer talks to the Wi-Fi access point, it's like this, right? So for example, let's say this is your computer and this is a mobile phone, right? And then so these two nodes cannot talk to each other, right? So this node does not have the information of others. There's no information sharing. So this is a multi-terminal system, or this many-to-one communication. That makes sense? Okay, so this is a multi-terminal system, right? For this kind of thing, if you want to analyze the capacity of that, so there's another course called network information theory. Okay, so yeah, just to be clear on what we mean here. Okay, so for the parallel Gaussian channel, so it's still a one-to-one communication system. Therefore, you can use the mutual information to characterize the capacity, right? If you maximize it, right? So now the constraint is this one, right? So before, and the only constraint is the power is less than P, right? But now, it's a summation of the power of all the channels, less than or equal to P, okay? Then you can formulate this optimization problem. Okay, and this is a typical convex optimization problem, so we can use the KKT condition to solve it, right? And then the solution is like this. So we have a water filling solution, right? So basically the P will equals to nu minus the variance of noise, and then we take the maximum between this guy and 0, right? It basically means that if nu is bigger than ni, and then we allocate some power, right? But if nu is less than ni, then we just put 0 power for that channel, okay? And it's called water filling algorithm, okay? So we give a sketch of it, and application is OFDM modulation. Okay, okay, so we didn't cover that here, right? But we do have the result that if the noise is colored, So the principle is exactly the same. So what we do is whitening, right? So basically, we can do the eigenvalue decomposition of the covariance matrix of the noise, right? And then, so this is the result, okay? And this Q is order normal matrix, right? So just multiply Qt on the left-hand side and the Q on the right-hand side, and then we can do a whitening process, right? Therefore, for the signal, so we also multiply a Q on the left-hand side and the Qt on the left-hand side and the Q on the right-hand side, right? So then the signal is changed a little bit, but after that, the noise will become only diagonal values, which is this lambda here, okay? And AII is after the whitening process on the signal matrix, covariance matrix, okay? Therefore, we have exactly the same optimization problem, and then we can solve it. Okay, it's very straightforward. All right, so yeah, just look at the book if you have doubts, okay? Then we came into chapter 10, so which is rate distortion theory. Okay, and we give all the definitions for the scalar case in our class, right? So here is the definition. So basically, we have for quantization problem, we have a quantization matrix, a quantization function, right? So what it does is that it maps from the source information to some indices here, okay? So this x could be continuous, could be discrete, okay? So, but those are discrete indices, right? Each of them represent a point on the codebook, okay? And f, of course, we have a decision region here, right? If x is in this region, then we just map all the x in this region to indices here, okay? So this is a decoding function. So it's to map each indices to a code here, a code word in the codebook, okay? And so in order to see how well we did for the quantization, so we introduced a distortion function, okay? So, and then we average the distortion function, we do the expectation of the distortion function over all the randomness, and then, so this is our distortion constraint, right? So as long as our distortion is less than or equal to something, some value, and then we're fine, okay? So you may imagine, right, so the more distortion we allow, so the less bits we need to compress, right? So, okay, and then we introduce, okay, so in order to solve this quantization problem, right, so we have two things to determine, right? One thing is the quantization boundary, okay, or this decision region, right? Decision region. Okay, and the other thing is that, okay, so now if we have a decision region, so what is the optimal point in this region to represent the signal? Okay, and we then say that, okay, so for the decision region, we want the Voronoi region, right? And for the optimal point, given the decision region, so we want the centroid there. Okay, therefore, given the region, so we can compute the centroid. So that's the optimal for this region. And for the fixed quantization point, we can determine the decision region again. Okay, so that gives you the Lloyd algorithm, or the k-means if you want. Okay, so in this way, so it's an iterative algorithm. You can do the boundary, and then the centroid, and then the boundary, the centroid, and so on. Right? Then so this algorithm will converge. That makes sense? Okay. The problem is that it may not converge to the optimal point. Okay, it will be some local optimal point. Okay, so that will be the scalar quantization. So now, let's continue. So today is our lecture 37, right? Yeah, we should have 39 total, so we'll have 2 more left after this one. Okay, so today we're going to talk about rate distortion. Yeah, we need to finish talking about quantization. And then we'll introduce you the rate distortion problem. And then, if I have time, so we're going to give some examples. So we'll probably not prove the rate distortion theorem, okay? But the proof idea is more or less very similar to before. Okay, I'll briefly mention it, but we don't have time to go over the details of it. All right, so yeah, we finished talking about scalar quantization, so now let's talk about the vector quantization. Or VQ. Okay, so the idea of vector quantization is very similar to the scalar case, right? The only difference here is that now the source information is a vector instead of a scalar. Okay? So basically here we argue that we use the same principle for the random vector instead of random scalar. Xn. Yeah. Okay, and then x taking values in Rn, right? So now, so in this case, so our encoding function is given by this, right? So it's from Rn to some indices, 1, 2, up to q, right? Which is the same as before, right? And for the decoding function, it is from the indices to the code word, right? So which is x1. So now all of this is a scalar as well, right? x2 up to xq. Okay, so this is pretty much the same as before, and you can see that each of them, so before it's in R, so now it's in RQ. Not RQ, Rn, or yeah, it's in Rn. Okay. Right? So this is the definition. Okay, so the code word definition, I mean the dimension of the code word will be the same as the dimension of the source information. All right? Okay, so now the question I want to answer is that why I want to use vector quantization? Right? Why scalar quantization is not good enough sometimes? Right? Why I want to use vector quantization? Yes.
If like the code word is a vector and we quantize that vector on the individual scalars, then we might not end up being able to reconstruct the vector that we started with. So we might end up with error because we don't get back the original code word.
You mean get back to the original code word? You mean original message?
Yeah.
Yeah, original message with some distortion. Yeah, we can do that, right? So for example, let's say, yeah, we just do a scalar quantization for each of those. Yeah, we can do that.
Okay.
It depends on the distortion, right? So yeah, just give a good distortion metric, right? We can do those.
Okay.
Yeah, so this is the main reason we do that is for more efficient, right? For example, let's say if we do a scalar quantization, so we do that like element wise. What does that mean? So it basically means that we're going to do that separately, right? So then we ignore some correlation among the elements. Right, so in a graph, you can think this way. Let's say if the vector length is 2, right? So we can plot that in a 2-dimensional graph, right? So for example, now, so x-axis is one element, y-axis is another one, right? Let's say if we do a scalar quantization, it basically means that we're going to have a quantized point here, 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 something like that, right? Let's say we do the exact same quantization for each element, right? So we always have this rectangle shape. Okay, but let's say if we can do a vector, so we can consider this plane, as a whole, right? So this basically means that we can do more efficient stuff. For example, let's say we can have a 1 point. How can I say it? Yeah, this is not a good example. Yeah, I'll do this. Yeah, it's okay, but yeah, I'll now draw this. I'll just draw the points here. Okay, so I can do 1 point in the middle, and I can do like 1 point here, 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 and or whatever, 1 point here. Okay, the boundary could be like this. right? If we're considering the, yeah, something like that. Right, you can see the shape here and the shape here is very different, right? And it is possible that we can put more information here. Okay, so it basically means that we can explore the correlation of the two coordinates, two elements, okay, to have more gains. Does that make any sense? Right? Think in this way, right? If we do element-wise, so this is what we end up with. We don't have any other option, right? But if we consider them all together, right? So then, we can place the shape whatever we want. Okay, so that's basically one of the reasons. So this is the scalar quantization, this is the vector quantization. Okay, so it's called shaping gain. Okay, we'll have some shaping gain here. All right, and in terms of the distortion, so we have the exact same definition as before. The D is defined as the expectation of the distortion between xn and x hat n. Right. For example, that can be equals to the mean square error, x n minus x hat n. Okay. So we can have the similar definition for the distortion. All right. Okay. So then, what is the problem of the vector quantization? Right. We know we can have. We can explore the correlation among different elements. Right, and we can have the shaping gain, okay, but what do we lose? Right, we lose, this could be more complex, right? So, do the same thing for each element is easy, right? This it can be more complex, right? And also, there's a higher chance that we achieve a local optimal point, okay, instead of global optimal point. Okay, so the problems, so it's more complex, and then, so we may achieve local minimum. Okay, so that's some problem. Okay, so those are definitions for the scalar quantization and the vector quantization. So now, based on this, let's introduce what is the rate distortion theory. So what is a rate distortion formulation by Shannon? Okay. So you may imagine that. I think you may kind of formulate the problem, right? So it's a source coding problem, it's a compression problem. We'll just formulate this in the same way as before, right? But the difference here is that we need to take consideration of the distortion, okay? And there's no big difference. Okay, so yeah, I'll repeat it and emphasize on the difference. So first of all, we consider a RID sequence, okay? So now we do not need to consider whether the sequence is continuous value or discrete value. It doesn't matter really, right? So the requirement is that distribution of the source information is IID, okay? And you may imagine why we want IID, because for the construction, probably we're going to use the AEP, right? The typical set, right? That's the reason we want IID here. Okay, very good. So let Xn be an IID discrete random vector. Okay, so here, yeah, I think in the we may prove this in the discrete case first, right? But there's no big difference with probability distribution px. Okay. Okay. Yeah. Here we consider discrete alphabet, discrete distribution first. On the discrete and finite alphabet x. All right. Okay, so next we're going to define what is the lossy source code. a lossy source code with block lengths n and rate r is formed by an encoding function and a decoding function, right? Okay, so the encoding function is given by this. So we say it's fn because it's a function of n. Okay, and that is from x to 1 to up to 2 power nr. Right, this is a sequence of indices. Okay, and a decoding function. So decoding function gn, so that is from all these indices to the code word x. Okay, so we call x hat. Is the reconstruction alphabet. Okay, so this is the rate distortion problem formulation, right? So we didn't talk about distortion yet, but so here one thing to notice is that so for the alphabet xn and for the reconstruction alphabet x hat n, so are they the same? Normally, right? So x n, or you would just need to say x and x hat. So normally, are they the same? Or they're not the same? I mean, alphabet. Yeah, probably not the same, but yeah, they could be the same, right? But yeah, they can also be different, right? Think about this, right? So if they're the same, right, probably or so the distribution of each element is different, then we can save a little bit, right? But but if x is a continuous random variable, right, then as our example before, as our quantization example before, so they are different, right? X is continuous, x hat may discrete. Okay. All right, so they are not necessarily the same. Okay, they could be different. All right, very good. Okay, for the distortion, it's a bit tricky here, right? So we see we give an example here, right? So this means what? It's an L2 norm, right? So this means that we compute this for each element and square them and then add them together, right? So basically, in rate distortion theory, we only consider this kind of distortion. Okay, it's pretty restrictive, right? Think about this, right? So basically, we ignore the correlation among all the elements, right? We just compute each individual distortion and add them up. Okay, it's very restrictive, but that is what we think, or what we're gonna consider here, right? The reason is because it is the simplest kind of distortion we can ever imagine, and even for this kind of distortion, the problem is hard enough. Okay, so this is called additive distortion measure. Okay, so the definition is as follows. So the distortion is from here mapped to a R, right? Okay, and then so we let x is in x and x hat is in x hat in, right? Then the distortion is defined as follows. So this is a summation of all the distortion of each coordinates, and then we'll average them. Okay, so this is the additive distortion. So we're going to add all the individual distortion all together, And here we assume that the maximum of this guy over all possible x and x hat. So this is less than infinity, right? Means the distortion is bounded. So we don't consider the case where the distortion is infinity. All right, okay, and then the average distortion. So D is given by this guy, okay, which is the same as before. Okay, so this is the definition of the rate distortion of the distortion. Okay, additive distortion. Okay, so we have not defined the rate yet, right? So we're going to define that later. So here, let's see some example, right? So in practice, we only consider, not in practice, in our class, so we'll only consider two types of distortion, right? So one type is called Hamming distance. Hamming distance matter, right? So when we talk about the Hamming distance matter, so we constrain the source of a bed and the reconstruction of a bed are the same. Okay, and then the distortion defined as follows. So basically, we say this guy is 0 if x and x hat are equal. If this guy's 1, this guy's 1 if x and x hat are not equal. Does that make sense? Right? This is very, very simple. Therefore, if we do an expectation of this distortion, what do we get? Right? Let's say we compute the expectation of this distortion. What does that equal to? Right, so basically this distortion is an indicator, right? So it's 1 if they're not equal, it's 0 if they're equal, so this equals to?
It's like this, yeah.
What?
Which probability that they're not the same.
Exactly, the probability that x and x hat are not equal. Okay, so that's the Hamming distortion. Very good. Okay, and the second distortion is what we have seen before many times. It's a square error distortion. Square distortion matter, and here in particular we still consider x and x hat, they're all in R. Okay, and the distortion here basically means the mean square error. Yeah, now we consider scalar here, so we don't need to write double bar, so just absolute value between this guy. Absolute value of x minus x squared. Okay, so that's the definition of square error distortion matter. Okay. Any questions so far? Okay, great. So now let's define what is the rate. Okay, so now we need to introduce what is the rate distortion theorem. Okay. We say a rate distortion pair. So that's given by R and D, right? R is the rate and D is the distortion, right? So basically, what we want to do is that we want to minimize the rate, right? Which is the number of bits we need to encode, okay? So we need to minimize the rate subject to a distortion upper bound, right? So that's pretty intuitive. So we say a rate distortion pair is achievable if, similar as before, we need to say there exists a sequence of code of rate R and increasing block length n, such that so the distortion so it needs to be upper bounded, right? So here, since we're increasing n, we consider limit where n goes to infinity. So this guy will be less than or equal to d. Okay, so this d is a d we consider here. Okay, so as long as the average distortion is less than this d, okay, then we say it's achievable, right? Okay, so yeah, this is in plain words, but mathematically, so it means the follows. So basically, it means that for any epsilon bigger than 0, right, there always exists n, and the code, we say fn and gn, so the encoder and decoder, okay, of block length n, such that, okay, so here, so we want a what? Right, so here basically we want an upper bound. Right, the rate, as long as the rate is less than this guy plus epsilon, and average distortion less than d plus epsilon, and then we say it's achievable. Wait, is that right? Yes, it's right. Right, so basically we say we can achieve rate R. It basically means that we can get a little bit higher than R, right? Okay, very good. Okay, so the next definition is these pairs, right? So this means that so this pair is achievable, okay? And next, we need to define, so what are other points that is achievable, right? So here we say R and D is achievable. Okay, so now let's see what are the regions, definition of the regions. So the rate distortion region for a source xi, okay, distortion measure D, and reconstruction alphabet x hat. Okay, so this region is defined as all the points that is achievable. In other words, it's the closure of all the achievable points. Is the closure of all the RD achievable pairs. Okay? So in other words, this means that if, let's say, RD, so that's a single point there, is achievable, then, so anything R prime bigger than or equal to R and D prime bigger than or equal to D, it is also achievable. Right, so intuitively, basically means that, okay, if RD is achievable, then if we have a higher rate and a worse distortion, then of course that is achievable, right? So normally, the rate distortion pair curve look like this. So here is a distortion, and here's the rate. So normally it looks like this. Okay, if we have a higher distortion, then we're gonna have a lower rate. Okay, and anything above this curve, the closure of it, so that is achievable. Okay, so this is a rate distortion region. Okay, and lastly, yeah, let's talk a little bit on the distortion function and distortion rate function, right? So if we draw a function this way, in this way, so that's a rate distortion function. So which means that so this is RD. Okay, but we can do the inverse function as well, right? So the rate distortion function is defined as RD. So that's basically the infimum of R such that RD is achievable. Okay, on the other hand, the distortion rate function is defined as dr. So that's the infimum of d such that rd is achievable. Okay, so that's pretty straightforward. Okay, so now we know what is, normally in practice, we always write R of D. Okay, so they are related, of course. Okay, so now let's introduce you the channel coding theorem. Okay, so this is the lossy source coding theorem for the DMS sources, DMS source, discrete memory source. Okay, and this RD, basically that equals to what? So actually it's equal to this. The mutual information between X and X hat. Okay, and then we're going to minimize this mutual information. Okay, and what is the variable, right? So remember, so the channel capacity look very similar to this, right? But for the channel capacity, what we do is that we maximize the mutual information between X and Y subject to, or the variable is the distribution of the source, X, right? But here is a source coding. The distribution of the source is given, right? So we need to determine what? The distribution of X hat, okay? Therefore, the optimization variable here is the distribution of X hat given X, right? Because X hat and X has to be related, right? So we'll optimize over that, and then we have a distortion constraint. Okay, so this is the Shannon coding theorem. Okay, any questions so far? Okay, so now let's see. You can see that, as we said before, there are a lot of similarities between this and the channel coding theorem. Okay, so let's recall the channel coding theorem. Maybe let's do that in the next page. Okay, yeah, for the source coding theorem, we can see that so Px is given, and then our goal is to minimize it over this random variable, right? So this is a variable. Okay, so that's a variable. So the variable is basically tells you how can we design the code, right? So this is a coding strategy. Right? Okay, so this is our current problem, right? And for the channel coding problem, let's recall that. For the channel capacity, so what we do is that the channel capacity equals the maximization of the mutual information between X and Y, where X is the source and Y is X is the transmitted signal and Y is the received signal, right? So we maximize that over Px. Okay, and that is a source, okay? And if it's continuous, so basically we're going to maximize it subject to a power constraint. Okay, And here, so for this problem is to minimize this subject to this constraint. Okay, and if we if we think about this, so this can be understood as a summation of a bunch of, distortion, right, and then average the distortion and then make it less than or equal to D. Okay, and similar here, right, we can also do that, right? So this is basically something like this, xi squared, right, and then this less than P. Okay, so the point is that this form and distortion can be very similar. Okay, not the same function, but kind of similar. Okay, therefore we can rewrite that in this way, right? So we maximize the mutual information, right, and subject to px. So where px we can write in this way. Okay, so basically, we can imagine, so this guy is bx, and this guy is basically b. Okay, something like that, right? So in this case, so what we can say is that py of x is given. Okay, and this is a channel. Right, and px here is the variable. Okay, and that is our coding strategy. Okay, and you can see that for this problem and this problem, right, they're very, very similar, right? So here's the minimization of mutual information, but here's the maximization of mutual information, right? And but here, so this is the variable, right? Or let's say, so this is a variable and this is a given, right? So this guy is the opposite. So this is a given, and this is a variable, right? So this is a channel, right? So basically we have another name for this guy, right? So this is called test channel. Okay, it's it's a given x. What is x hat? It's also kind of like a channel. Okay, so actually you can see that. So the channel coding problem and rate distortion problem, they're like a dual problem. Okay, if you remember what we discussed for the mutual information, so remember that for the mutual information, if we fix py given x, and then so this mutual information is a concave function of px, right? On the other hand, for this guy, if we fix px, and this is a convex function of this guy, therefore we can do the minimization problem. Okay, therefore probably we don't have the time to derive everything, but you can do the same idea as before to derive a formula how to compute it, right? Use the KKT condition. Okay, but that is incredibly complicated. Okay, so great. So now, given all of this, so let's see an example. Okay. Okay, we're going to see first example, right? The first example is the binary source with Hamming distortion, and the second example is a Gaussian distortion. Okay, so Gaussian source with, not Gaussian distortion, the Gaussian source with the mean square, the squared error distortion. Okay, so the first one is binary. So this is a discrete case, binary source with Hamming distortion. Okay, in this case, we have x equals to x hat, so that's 0 and 1. Okay, because we consider binary source, right? Only 0 and 1 counts. Okay, so here, let's assume that the probability that x equals to 1 is p. We'll assume that is less than half, right? Okay, and then the probability, you'll see why we assume this, right? If we don't assume that, it's also okay, it's not a big deal. X equals 0 is equal to 1 minus p, right? So Bernoulli source. Okay, so now the distortion is as follows. So in this case, so we have a very nice expression for the Hamming distance, right? Basically, if it's 0, then x and x hat equal. right? If it's 1, then if x and the x hat are not equal. Okay, because we only have 0 and 1, so we may have a better expression of this, right? So basically we can use a formula here, right? So when it's only 0 and 1, so yeah, let's compute what is x plus x hat. Okay, so let's use the binary plus or XOR, right? So if that's the same, then x plus x hat equals to
0.
exactly 1 plus 1 equal to 0, and 0 plus 0 equal to 0, right? And if they are different, then this guy equals to
1.
exactly. Okay, very good. Yeah, now you may imagine, so why do we want this, right? Why we want this expression? So basically it represents a what? A channel. Okay, so we can relate this to our communication problem later. Okay, so now let's derive the mutual information, right? So the derivation here is not extremely straightforward. So in order to derive mutual information, so again, so we have two ways to expand it, right? So when we want to maximize it, we can do hy minus hy given x, right? And then characterize hy is challenging, right? So here we do it the other way. So we expand it using this. Okay, and now computing this is easy, right? But we want to maximize this may not be very easy. Okay, so let's see. So it's the binary source, right? So basically, the entropy of x is the binary entropy function. Binary entropy function. So we use this notation to represent it, right? And then, so now we're gonna use this formula here, right? So basically, x. So let's say because we know x hat, right? So we can write in this way, right? Then it will not change, right? Because we're adding something we know, the entropy will not change. Okay, and then we can have a lower bound of it. So we just ignore the condition. Okay, we drop the condition here, so we have a lower bound. Okay, and what is that? What is x plus x hat? Right, see here. So that's basically the distortion, right? Because when it's 0, this guy equals 0. When it's 1, this guy equals 1, right? So basically, this is nothing but the distortion. Okay, and then, so then the next step is to maximize this guy. Okay, so that's pretty hard. So I'll tell you the result directly. So this will be a lot bigger than or equal to this guy. Two. Yeah, the entropy function of the distortion D. Okay, and so now let me tell you what is the distortion function here. So this guy, what does this will equal to? So basically, it will equal to the follows. So RD will be bigger than or equals to this guy minus H2D. Okay, when D is bigger or less or bigger than or equal to 0, and less than or equal to the minimum between P and the 1 minus P. Okay, and it will be 0 otherwise. Okay, does that make sense? Yeah, so basically, yeah, we didn't show this formula, right? So just want to tell you. So basically, we can show this is bigger than or equal to this. And then, we can show that, so the distortion is bigger than or equal to this. So this is achievable. Okay, so, okay, let me explain one thing, okay? So now we want to compute this, right? So one interesting understanding is as follows, okay? So now from this observation, from here, so what we can see is that, okay, so now given x hat, we're going to determine the distribution of x. Does that make any sense? If we write it in this way, right? If we want to write it in this way, so it basically tells you that, okay, so given x hat, we're going to determine the distribution of x. Is that weird? Yes, it is, right? Because what we want to do is the opposite. So we want to determine this. Given x, what is the distribution of x hat? Right, but here, if we write mutual information this way, so it's the opposite, right? Right? Okay, so therefore, our following optimization is artificial. It's a purely mathematical effect. Okay, so now basically, in order to maximize this guy, so that's our goal, we need to, given x hat, we need to determine a distribution of x. Okay, in other words, so we can do it as following. Okay, so basically, we can model x equals to x hat plus e. Okay, what is e? Is the error. Okay, and we can assume that because error is basically is our distortion. Remember, what is d? D is the expectation of that. D is the probability that they are not equal. Okay, therefore, the probability of they are not equal. Can you tell me what is the distribution of, what is the distribution of E? What's the distribution of error? Right? Distribution of error, so D is the probability that they are not equal, right? Error E is like Bernoulli distribution. It's either 0 or 1, right? If E is 1, if E is 0, there's no error. If E is 1, there's an error. But the probability of making an error is what? Is the expectation of the distortion. So that's basically D, right? So basically, it follows a Bernoulli of D, right? So what does that tell you? What does this notation mean? Did you see that before in chapter 7? That's chapter 7. Chapter 9? Yeah, y equals to x plus a noise. It's a channel. It's a communication channel, right? Then we can artificially build a communication channel. So here is x, here is x, here is x hat, here is x, right? And for the x hat, we have 0 and 1. Okay, and x, we also have 0 and 1. And with the probability of d, we're making an error. With the probability 1 minus d, we do not make any error. And the same here. Okay, same here. So we have d here, 1 minus d. Okay, and we can, we know the distribution of x is p, 1 minus p, p. We can assume the distribution of x hat is 1 minus q, q here. Okay, so did you see this kind of channel before? Right, BSC channel, binary symmetric channel, right? And for this specific channel, we call that backward channel. Right, because forward is, given x, we want to know x hat, right? But it's the reversed way. It's called backward channel. Okay, so then we can use that to determine, the value of q and so on. Okay, and then we can have our result. Okay, so you can see there are a lot of connection between rate distortion and channel capacity. All right, so yeah, so let's end for today.